All right, guys. So next, let's look at what we call Rayleigh criterion. This one assumes that instead of one source generating the light that goes through an opening, now we have two sources. For example, here I have source one and I have source two. That means through the opening through one slit, you have two different uh, light, could be even different wavelength of light. So they don't have to be coherent. They can be non-coherent. Then when they go through those two openings, then what you see here, you see diffraction patterns. Okay. Now, one of the things we have here is what type of diffraction pattern you will see and what will be our ability to distinguish those diffraction patterns of each source will depend on how close those sources are to one another and would depend on this angle theta. All right. So you can see that you have, image A and image B. What we have for image A is the theta is relatively large. Source one and source two are far from one another. And then you see, you know, diffraction pattern for the source two completely separates from the diffraction pattern of source one. And what you will see here then in terms of you will see that let's say this one being exactly at the, right below the peak over there, this one exactly at the peak of the second one, but you will be able to distinguish both of those patterns. Now, for the image B, then source one and two are very close to one another, and theta is too small compared to theta in image one. And then when the light goes through the opening of those source one and source two, they generate two diffraction patterns, but those two diffraction patterns are too close to one another. And if you view it on the screen, you might not be able to distinguish them. Okay. So those images might not be what we call resolved. All right. That means what we're going to be looking at here is what are the sort of like the minimum requirement for the our system to be able to distinguish those two sources. And this is generally very important for astronomy, where you have two stars far away from one another, and when you look at the star, or not necessarily far away, but two distant stars, when you look at those distant stars, if they're too close to one another, our optical instruments might not be able to distinguish them, might not be able to separate them. And instead of like, let's say two stars like this, if they're too close, our optical instruments might show us like, let's say one blob. So like, let's say one bright spot without necessarily being able to distinguish which one is star A, which one is star B. We might not even be able to tell that there are two different stars. So those are the important things that we're going to be now looking at. All right. So again, in terms of then what we have here is our goal here is to make sure that theta here is large enough so that we can distinguish those two diffraction patterns. That means we need to have some kind of minimum, let's say, angle theta, right? For which we can then have um, pattern for a diffraction pattern for source one separate from source two. All right, that means what we have here is this. When the central maximum of one image falls on the first minimum of another image, the images are said to be just resolved. This limiting condition of resolution is known as a Rayleigh criterion. So that's why you can see, right? So what we have over here, that's the requirement. So that the central maximum of one image falls on the first minimum of another image. Okay. In that case, we should be able to see. And that's kind of like what we have over here, right? So this is the first minimum and this is the first maximum. And it doesn't fall on that. That means, like let's say what we have is that this is not on top of the other one. That means it's going to be hard for us to distinguish the patterns. So we need at least, have this one right here so we can be able to, separate them. All right. So that's kind of what we have in this image. That means the Rayleigh criterion to determine minimum angle of separation, theta minimum, subtended by sources at slit for which images just resolved. First minimum in single slit diffraction patterns occurs at an angle for which we have the sine of theta. Remember, this is sine of theta equals m times lambda over a, but we're taking m equals 1 for this to be the first minimum, and a being the width of the slit. So then we can look at this to be the minimum, right? So this is the minimum angle theta what we want that we want. Generally, the sine of theta is approximately theta. So then we can just replace theta for sine of theta with theta, and then we can say that theta minimum is equals to lambda over a, where m is assumed to be 1 in this case. All right. So that means this expression gives smallest angular separation in radians, right, for which two images resolved. Because lambda is much smaller than a in most situations, sine of theta is small, so we can use the sine of theta approximately theta. Okay. That means this is the limiting angle of resolution for slit of width a. So if in order for us to be able to separate, that means we can use this uh, information about the wavelength of the light and then the width of the opening of the slit to calculate this theta minimum. Okay. And for any theta that is greater than this, we will have no problem separating. Any theta less than this, then we're going to have a difficult time separating those two sources. Okay. All right. So in a way, then we can have two different, let's say, openings, right? So we can have a slit, or we can have a sort of like a circular, opening. So now the equation that I showed you, that was for the slit. That means if I come back here, I can say that this is for the slit. Okay. So for the slit, we can then use this equation to calculate the minimum angle, okay, or the limiting angle. Whenever we have then a circular apertures, that means our opening, sort of like, let's say maybe it's a, something like this. An opening is like a sort of like, let's say, circular rather than just a slit. In that case, then the theta minimum is equals to 1.22 times lambda over d, where d here is then the diameter of the aperture rather than a, which is the width of the slit. And then 1.22, it's a information that comes from the mathematical analysis. So it's basically something that is beyond the scope of this class. So just think of it like, let's say this is just always part of the class, part of the equation if you dealing with the circular apertures. Okay, that means the difference between slit and circular apertures will be if the problem tells you the width of the slit relative to the, let's say, compared to the diameter of the, let's say, aperture, right? So then it will, you will be able to understand if you're dealing with the, just a single slit or just basically the circular aperture. Okay. So again, you can see in the diagrams we have A, B, and C. So A gives you the sources that are far apart and the patterns are well resolved, right? So you can see two different, let's say, diffraction patterns. Um, and you can see that the requirement was that the minimum of the first one, right, you know is more or less um, sort of like, or the maximum of the second one is above or further from the other pattern than the first minimum. That means what you have here is this is the first maximum of the second pattern, and it is basically a little bit to the left of the minimum of the first pattern, where blue is the first one, red is the second one. Here, this is basically um, the dark spot, right? So the first minima of the blue wave, let's call that. So then this is the red, where you can see that right now what you have here is this is sort of like, let's say, the minimum you can have, where the maximum of the red is right on top of the minimum of the blue. That means here you can say that this is what we call just the minimum requirement to satisfy the Rayleigh criterion. And after that, if let's say here's the minimum and here's the maximum, what you're going to see is you're not going to be able to separate them. Okay, so this is what we get, even though there are two sources, but we can't really separate them because they're too close to one another, and an angular distance between them, right, is just smaller than the theta minimum. So here's two images. On the left side is the image of Pluto and Charon, which is the moon of Pluto. So this is taken, you can see, right, in 1978. So at the time, the image was taken probably some kind of Earth-based telescope, and what we have here is you can't really separate them. You can't separate Pluto from its moon. So what we see here is sort of like a one blob. Okay. So then obviously, the one of the biggest factor over there was atmospheric turbulence. Okay. When we had then the Hubble telescope start taking pictures above the atmosphere, so then this uh, basically the problem that we had with the Earth-based telescope basically went away, and then you have much clearer, let's say, view of the space around it without the atmospheric turbulence. So then obviously the Hubble Space Telescope also had a much better optics, and so we were able to take pictures, and you can clearly see then the Pluto and Charon, the moon and the planet. Well, right now it's a dwarf planet, but still, you can clearly see the Pluto and its moon resolved as two different, bright objects. All right, so let's look at a few examples here. What is the approximate size of the smallest object on the Earth that astronauts can resolve by eye when they are orbiting 250 kilometers above the Earth? Assuming lambda is equals to 500 nanometers and a pupil diameter of 5 millimeters. Means the light entering your eye, right? All right, so now in this case, obviously our eye is, we can model the circular, and you're given the diameter as 5 millimeters. That means that's basically the example of a circular aperture, right? So we can then say the diameter is 5 millimeters. Okay. Wavelength is 500 nanometers. Okay. And then we're given basically distance, right? 250 kilometers. So this equals to 250 times 10 to the 3 meters. That's basically kilometers. All right. So then what we end up with is we want to calculate the approximate size of the smallest object. So then, well, let me actually use L for the, 250 kilometers. So this is in terms of then um, calculating the theta min, which is equals to 1.22 lambda over d. Okay. So, and one of the things we can have here is, since sine of theta is equals to lambda over d, and approximately tangent of theta, which is then equals to then y over L, so then we can then just basically replace lambda over d with y over L. Okay. So basically, that in a way, like those are equal to one another. Sorry, I missed 1.22 over there. All right, so that means one thing I can say here is theta min, which is equals to 1.22 lambda over d, then is equals to y over L. Okay, basically using that small angle approximation because they all equals to a theta. Okay. That means what I have here, 1.22 lambda over d is equals to then y over L. Okay, where y is basically that size that we are looking for, which is approximate size of a smallest object. So rearranging this, then y is equals to 1.22 lambda L over the diameter. Okay, then 1.22 times the 500 times 10 to the negative 9 meters, then times the length, which is 250 times 10 to the 3 meters, then divided by the diameter, which is then 500 times 10 to the negative 3 meters. Okay. So then we can calculate y to be 30.5 meters. That means if the object is 30.5 meters, then we'll be able to see it, um, like the features of the object, right? So it will be sharp enough for an astronaut to understand what he's looking at. It has to be like about 30.5 meter long. That's the smallest object astronaut can resolve. Okay. Here's another example. Um, an impressionist painter, George Seurat, created paintings with an enormous number of dots of pure pigment, each of which was approximately 2 millimeters in diameter. The idea was to have colors such as red and green next to each other to form scintillating canvas, such as his masterpiece, A Sunday Afternoon on the Island of La Grande Jatte. All right, so I have an image of that in the next slide. Assume that lambda equals 500 nanometers and a pupil diameter of 5 millimeters. Beyond what distance would a viewer be unable to discern individual dots on the canvas? And that's kind of like the idea. So if you're too close to to this canvas, you'll be able to see those individual dots. Okay, but when you go back, then you basically not able to distinguish these dots, so then you can see the entire image. So like, let's say, kind of continuous, the colors, right? Going back and forth between green and yellow and things like that. So anyway, so kind of like that's sort of like the point of this type of image, that some of those impressionist images, right? You have to look from a little bit a distance, so that you can actually be able to enjoy them. Anyway, so here's the image that we have. So again, if you kind of like look at very closely, you should be able to see those dots. Okay, but if you kind of go back, then you're unable to see those dots individually anymore, and then you, I guess, end up admiring the painting. In terms of then, what we want to do here is we want to let's say then calculate the distance. Okay. Again, so this is in terms of since we're talking about the wavelength and we're given a diameter, it means, d is equals to 5.00 millimeters, which is 5.00 times 10 to the negative 3 meters. Wavelength is 500 times 10 to the negative 9 meters. And then we want to find basically the distance. Okay. Again, when the pupil is wide open, then it appears that the resolving power of human vision is limited by coarseness of light sensor on the retina. Okay. So what we have here is we can then calculate the theta minimum, which is equals to 1.22 lambda over d. But I showed you in the previous example is that we can also say that this is equals to d over L, where d is basically the y, right? So y over L or d over L, which is the distance, right? The size. And then we can just again, so d is the distance um, between those dots. L is then the distance that you will be standing. So like, let's say this would have been in terms of, if this is, let's say, remember, if this is like, let's say the slit and this is the screen, this is the L, right? The distance. But if talking about, let's say, the human eye, right? Here's the pupil. So how far away you should be in order to, not be able to see those, or the minimum amount of, to see those dots. All right, so they're rearranging, solving for L. So this will be then d times diameter over 1.22 times the wavelength. So then 2 times 10 to the, that's 2 millimeters of, I did not write it down. So d is equals to 2 times 10 to the negative 3 meters. Then times the diameter, which is 5 times 10 to the negative 3 meters. Then divided by 1.22 times the wavelength, and that's 500 times 10 to the negative 9 meters. All right, so calculating 16.4 meters. Okay. That means beyond what distance would the viewer be unable to discern individual dots? Well, 16.4 meters. That means if you're, about 20 meters from the painting, then you should be able to admire then the painting without being able to resolve the individual dots. All right. Again, it's a beautiful painting. All right. So the next thing we're going to talk about here is the diffraction grating. All right. So for the diffraction grating, what we have here is we have not a single slit, not double slit, but n number of slits, which is generally relatively large. So, and they're very useful, especially when you're talking about spectroscopy and things like that. So, uh, thing like this. So the idea for this is kind of similar. You have the light incoming, plane wave of light coming in, and then instead of like let's say one or two slits, then you have basically sort of like an n number of slits, and then the light goes through that, and you can see, right, so you see the sort of like a pattern. So there's a central or the zeroth order maximum, m equals 0, and then there's a first order maximum, and then the first order maximum on the other side. That means you have these are for the maximum. So you have a constructive interference, m equals 0, and then another 2, m equals 1, m equals minus 1, another 2, m equals plus 2, minus 2, and so on and so forth. So that means, what we can do here is kind of go back and looking at the maximum as we did for the double slit. All right, so okay, so right, you have transmission grating, so made by cutting parallel grooves on glass plate with precision ruling machine. So spaces between grooves transparent to light, act as separate slits. And then we have a reflection grating made by cutting parallel grooves on the surface of a reflective material, and reflection of light from spaces between grooves. Specular, remember there's a specular and diffusive, right? Reflection. So specular means, it's smooth surface, so all the lights are parallel to one another, and reflection from grooves cut into material diffuse. So you can have either one or the other one. All right, so you can see then what we have is that current technology can produce grating that have very small slit spacing. Okay. And one of the things we have about diffraction grating is that sometimes you want to look at in terms of how many grooves per distance you have. So let's say grooves or lines or grooves per millimeter or per centimeters and things like that. For example, typical grating ruled with 5,000 grooves per centimeter has slit spacing of, so what you do, you take then D, which is the spacing between uh, the slits, to be 1 divided by how many grooves per length you have. So if you're told that you have 5,000 grooves per centimeter, then you take D is equals to 1 over 5,000 to get the distance between the slits, which is 2 times 10 to the negative 4 centimeters, or about 0.2 millimeters. All right, so one thing we have about the diffraction grating here is that generally the theta is very large. So one of the things we have here is the mathematics, right, of the diffraction grating is pretty much identical to the mathematics of the um, let's say for the bright fringes, right, to the double slit. That means we have d sine theta equals m times lambda, where m equals 0 for the central one, plus minus 1 for the first maximum, plus minus 2 for the second order maximum, plus minus 2 for the third order maximum, and so on and so forth. Okay. The only difference here is theta cannot be considered as theta small anymore. That means sine of theta will not be equal to the theta, will not be equal to the tangent of theta anymore. Okay, so this basically just gets thrown away for the diffraction grating. That means what you end up with here is always calculating in terms of the sine of theta, in terms of the, our equivalent, right? So y is equals to L tangent of theta. Okay, that means you're stuck with those equations, right? So yes, you can calculate the theta from this equation, right? For example, the theta is equals to inverse sine of m lambda over d. Yeah, you can do that, right? So you can calculate the theta, and then the same theta then can be used here to calculate the, let's say the vertical position, right? For the first order maximum, second order maximum, and so on and so forth. But the idea here is that you cannot combine them into, uh, let's say, one equation where then what you have here is sine of theta, tangent of theta is approximately theta. That's basically no longer applied here. Okay. So, but in any case, the idea here is whenever you are calculating the angular position, So here you can, pretty much this, remember, so this will be in degrees, right? So this will be in degrees, no longer in radians, because you are calculating from the inverse sine. Okay. So that means you have then angular position in degrees, and then linear position in meters for that. All right, so you can see what we have here is um, the m order maximum for each wavelength occurs at a specific angle. All wavelengths seen at theta equals 0, which is corresponds to m equals 0. The first order maximum m equals 1 observed at an angle that satisfies relationship sine of theta bright equals lambda over d. Okay. So then the second order m equals 2. So then equals to then sine of theta bright is equals to 2 lambda over d, right? And so on and so forth. That means what you have here is this, this is m equals 1, this is m equals 2, and so on and so forth. Okay. And one of the other difference here is when we're talking about the pattern that we see on the screen, um, because you have so many slits, right? The I already mentioned it earlier, is that the larger the number of slits, more narrow are going to be the graphs for the intensity of the light, of the pattern that you see. So for example, here you see double slit. Okay, you can see, right? So what you have here is you have the central one, and let's say here's IMAX, right? And this, what you see here is the distance between them, right? And compared to that with the diffraction grating, right? The Those graphs are much more narrower. Okay, so you can see compare sharpness of the principal maximum, broadness of dark areas compared to the bright fringes, characteristics of two slits interference. Because principal maxima are so sharp for grading, much brighter than two slit interference maxima. Okay, so it means instead of like being like this, they kind of go like that. Okay, so like in terms like that. All right, so generally what we have here is that diffraction grading is very useful for it has very useful applications. So you can see, right, one of the things we can do here is a way to measure the wavelength of light is called diffraction grating spectrometer. Okay. The collimated beam is incident on the grating. The diffracted light leaves the grating, and the telescope is used to view the image. So one of the things we can do here, we can use this to basically look at the light coming from a distant star and then get information about it. So we can be able to see the type of signatures of the light, the type of, uh, let's say the molecules or gases it interacted with. We should be able to, we usually use diffraction grating in experiments, right, in the laboratories to look at, for example, hydrogen, and look at very specific signature of hydrogen compared to helium, which has a very specific signature. And diffraction grating allows us to see those patterns, because when the light goes through hydrogen, it basically has very unique signature, because we have different, let's say, wavelengths, right? Different, let's say the different absorption and emission, so like a pattern for those. Okay, so you can see the wavelength can be determined by measuring the precise angle at which the images of the slit appear for various orders. So we have also, the atomic spectroscopy, where the light from an atom is analyzed and used to identify the atom. So that's kind of what we have. That means you can look at the distant star, look at the light coming from a distant star, and using atomic spectroscopy, you know, uh, figure out what type of uh, elements present in the atmosphere of that. So you can look at in terms of, does it have hydrogen? Does it have helium? Does it have, I don't know, let's say carbon, and so on and so forth. And all is done by looking at the light going through the diffraction grating, because then you can pretty much, do the, like let's say the atom is analyzed and used to identify those things. All right, so let's look at an example here. Light from an argon laser strikes a diffraction grating that has 5,310 grooves per centimeter. The central and first order principal maxima are separated by 0.488 meters on a wall 1.72 meters from the grating. Okay. Determine the wavelength of the laser light. Okay, so that means what we have here is we're given in terms of number of grooves per centimeters. Okay, so which is 5,300. So that means we have 5,310 grooves per centimeters. And then we're told that the central and first order maxima have a separation of 0.488. Okay, so that means we can take this to be the y, which is the vertical position, right, between between them. So think like this. So I don't know. So let's say something like this, and let's say here's the screen, and I don't know. I guess I will. I should have. Let me use different colors. So then red I'll use for the bright. All right. So let's say. So these are my diffraction grating. Here's the screen. Let's say this is L, and what I have here is that this is my central one, and then let's say this is my first order, right? That means I can say that this is m equals 0, this is m equals 1, and their distance between them is given as 0.488 meters, which is, y1, right? So that means that the position of the first maxima relative to the central one. Okay. And what we have here is that L is 1.72 meters. And then in terms of this information is information about basically way of finding D, which is the distance between the slits. Okay, so again, y is 0.488 meters. All right, so next let's then do this calculation, because one of the things we have d sine of theta is equals to m times lambda. Okay, remember where n equals 0 plus minus 1 plus minus 2 that. Okay, so when m equals to 1, and that's what we have, right? So d sine of theta is equals to just lambda. Okay. So, but we also have where L tangent of theta is equals to y. Okay. Remember, so we cannot use a small angle approximation anymore. So that means one thing I have here is this is the equation that I need for the wavelength, because that's what we want, right? It means I need to d sine of theta gives me wavelength. I have d, at least way of finding d, but I don't have theta. So, but I can use L tangent of theta because this is equals to y, and I'm given y to find the theta. Because from here, then tangent of theta is equals to y over L, and then the theta equals inverse tangent of y over L. Okay, so inverse tangent of y is 0.488 meters divided by L, which is 1.72 meters, and I can calculate this to be 15.8 degrees. So you can see, right? It's a large theta, so I can't use the small angle approximation. All right, so now that I have this, next thing I will need to do is to find d, but d is always equals to 1 divided by number of grooves per centimeter. So let's say in this case 5310. See, like let's say grooves per centimeters, and if I calculate this, so I will get 1.88 times 10 to the 3 well times 10 to the 3 nanometers. And I will explain why I'm using nanometers here. So you can calculate in terms of centimeter, but convert it into nanometers. Because I know one thing, that the wavelength of the light is going to be some nanometers. And then when I write wavelength is equals to d sine of theta, now my d is 1.88 times 10 to the 3 nanometers, then times sine of 15.8 degrees. So my answer then will be 514 nanometers. So that will be then the value of this. Okay, that means I can calculate the wavelength of the light, and it's 514. So it's roughly a green color, right? All right. Okay. All right. So then the last thing we have here is polarization of light or light waves. One of the things we have here is the polarization is sort of like an application um, that was discovered, actually by the person that we already talked about earlier, and that was Arago, if you remember, right? Francois Arago, who gave us um, the experiment to verify that you will see a central bright spot at the center of the, you know, let's say circular, object. So he also, came up with experiment to, for the polarization. Now, one thing that we have about light is that we learned that light is a combination of electric magnetic, vectors, right? The waves. So you can think of, like, let's say, when you talk about light, it's electromagnetic vectors associated with an electromagnetic wave. And one of the, let's say, images that you would always see for the light is when you have, let's say, this is the z-axis, this is the y-axis, this is the x-axis. And then what we have here is, let's say, this is the electric field, which is generally considered to be a vertical. Let me kind of, so let's say here's the electric field, which is oscillates with time, right? And then this is then the magnetic field, which also oscillates with time. So then if I do this, like, let's say like that, you then can see that what we have here is sort of like, let's say, the wave pattern, right? So let's say the wave pattern of the electromagnetic wave, pretty much from here. But that means, in a way, what I can think of, like, light is always to be, electric field vertical and a magnetic field horizontal. But let's assume that this. So light always has, let's say, electric field like this, but it oscillates. It also oscillates like this, back and forth, like that, and so on and so forth. That means, YZ axis, right? The electric wave vector always oscillates back and forth on the y-axis. Same thing with the magnetic wave in a XZ axis. So that means the light is the electric. Let's only concentrate on electric. So then electric wave of the light always have, let's say, every direction like this, you know, along that, YZ plane. So it always have any direction you can think of. And it does one at a time, but it does so fast that when you look at it, you can think of, like, let's say, okay, so at every second it has some kind of direction. So you can kind of, like, have something like this. Okay. That means a direction of polarization is defined to be the direction in which the electric field is vibrating. So we can think of it like that. And since electric field is vibrating, every direction, we can call this unpolarized or natural light. So unpolarized or natural light. Okay. Now, then what we have here is, here's an image of that, right? So when you're talking about, let's say, then the natural or unpolarized light, right? It vibrates in all directions. So all direction of vibration from a wave source are possible. That means if this is some kind of light source, so that it generates electric field in every direction. So then if the light is moving, if like it's propagating like this, you can think, like, let's say it has all the direction. Okay. Again, so this is an unpolarized wave. Okay. And or sometimes we call it natural light. So now, one thing that we have here is, Arago was able to design a device that basically polarizes the light. Now, what does it mean, polarizes the light? So it's a device that basically takes the light, which has every single direction, right? And when the light goes through this device, so since I don't have much space in this direction, let me kind of do it in opposite direction. So let's say the light is moving like this. Okay. So then what we do here, we put some kind of device. So let's say here's a circular. Polarizer can be circular or rectangular, or, let's say it's a circular, polarizer. Now this polarizer has axis. Okay, so special sort of like, let's say, type of, polarized molecules and things like that. And it has axis that is, either horizontal or vertical. So basically things like this. So these are the axes of a polarizer. Okay, so right now it's vertical. So let's say that's the axis of a polarizer. Okay. So now, as the light then goes through the polarizer, okay, so everything there is parallel to this, all the light, there's the light basically parallel to the polarizing axis or axis of polarizer will propagate through. But other parts, other light, right, that are not parallel to that polarizing axis, or the plane of polarization, you can say, then end up being absorbed by the polarizer. Okay, that means again, only the light that is parallel to the axis of the polarizer will go through. That means what I have here is when the light comes out here, it's going to be polarized exactly same axis as the polarizer. Okay, so that means what we're doing here, we are linearly polarizing the light, and polarized light only has one direction. Remember, non-polarized or unpolarized light has all the directions, right? All the direction of vibration. Okay, but the polarized light now has only single direction because it went through a polarizer. Okay, now a wave is said to be, again, linearly polarized if the resultant electric field vibrates in the same direction um, at all times in the particular point. That means always same direction, right? So for example, vertical now, okay, and no more horizontal or other direction. So in a way, sometimes what we do is to simplify this, we say that it's a superposition of just vertical and horizontal, right? So ignoring everything else, because I can find the projection of this one along the horizontal, projection of this one along the vertical. So just have just those two, horizontal and vertical. Okay. Now imagine that if you have a light, unpolarized light, then you can say that it has both horizontal and vertical. And if it's moving like this, right? So then if it's moving on its x-axis, let's say, then if you have a polarizer with the axes that are, let's say, vertical, then when the light enters this polarizer, right, the polarizer then will absorb everything that is not parallel. In this case, the horizontal, it will absorb the horizontal, but then it will allow the vertical to go through. That means now light over here, let's call this point 1, which is the position where the light was unpolarized. And then here we have position 2, where now the light is then polarized. That means the light now propagating with just one direction. All right. So now, what can we do from there? Well, or what is the advantage? Well, think like this. One of the important thing about this polarizing the light here is that the intensity of light at point 2 is exactly half of intensity at point 1. And point 1, we assume it's unpolarized. So sometimes we just call this I naught or I max. Okay. So let's use I max. Okay. Or let's say I naught, for example. So then I naught is basically the natural unpolarized light intensity. Okay. And then as soon as it goes through a first polarizer, intensity is exactly half. Okay, exactly half, and it has one direction, so it's polarized. Well, next, what I can do here is I can put another polarizer. Let's say something like this. And then axis of this polarizer will then allow me to either have some of the light propagate through, or things like this. If polarizer has axis like this, when this light then enters my polarizer as vertical, well, my polarizing axis is horizontal, then everything will be blocked. So there will be no light. Okay, there will be no light. That means if you're looking through the second polarizer, a lot of times this is known as an analyzer. Okay, so then there will be no light. Okay, so this is a polarizer, and the second one generally called its analyzer. So then there will, and if the analyzer and polarizer are perpendicular to one another, you will see no light. Okay, that means you can completely block. That means intensity, let's call this 0.3. Intensity at 0.3 is equals to 0. All right. So again, so it's common to refer the direction perpendicular to the molecular chains as the transmission axis. So this is kind of like transmission axis, which is the axis of the polarizer. So an ideal polarizer, all light with electric field parallel to the transmission axis is transmitted. That means parallel to that transmission axis. All the light, with the electric field perpendicular to transmission axis is absorbed. Okay. Now, as I said, right? So here's a natural light. The first polarizer, basically, let's say having this, makes the light linearly polarized. And then the second one can block it. But for example, what if I don't want to completely block it? then what I can do, I can make this axis not perpendicular. So let's say again, so let me draw this axis like that. So think like this. Now what I have here is, this is, one, which is the region where the light was unpolarized, two, where the region is linearly polarized, and three, when I have the light going through the analyzer. So this is a polarizer, and this is an analyzer. And then what I have here is this. The analyzer doesn't have to be perpendicular to the, let's say, transmission axis, doesn't have to be perpendicular to the light. I can maybe have something, such that it has some angle theta relative to the, let's say, uh, the propagating light. Okay. Because now what I can have here is that how much intensity I will have at point 3. Remember, intensity at point 2 is exactly half of the intensity of the original light, unpolarized light. Then I3 will be equal to then I max, then times cosine squared theta. Okay, that means I max is the intensity before. In this case, it will be, intensity at point 2, right? Which is then 1/2 I naught. The I max is basically intensity, before it goes to the analyzer. Then cosine squared theta. We can see, right? When my transmission axis is perpendicular to the light, theta is 90, cosine of 90 gives you 0. Okay. But if it's not 90, it's like 30, 40, 60, then you have, basically some of the fraction of the light still going through. Anyways, that equation is known as a Malus's law. Okay. So Malus's law basically gives you the intensity of the light after the analyzer. Maybe you can have 4 or 5 different, polarizers, right? After the first one. So the first one generally is known as a polarizer. Second one is analyzer, and I guess you can call like analyzer 1, 2, 3, so on and so forth. Okay, because polarizer always just drops the intensity to 1/2, and then analyzers can drop it further. Let's say as much as you want. So like in terms of anyway, so that's kind of what we have. This equation, right, assumes that I max is the intensity, let's say before this particular, let's say this will be, for example, if I'm using this as as 2, then in this case, sorry, like let's say in terms of 3, right? Because I have 1, 2, and 3. Okay, so I don't use this equation for 2 because I know that I2 is equals to 1/2 I1. That's for sure. Then I use this always for 3. Then this is basically what I had at 2. Okay, times cosine squared theta. All right, so you can see intensity of the transmitted beam is maximum when the transmission axes are parallel. That means, this should be theta equals 0 or 180 degrees. And the intensity is 0 when the transmission axes are perpendicular to each other. This would be, this would cause complete absorption. That means no light then will propagate through. All right. So then what we have here is this kind of like, gives you that. You can see that, let's say here you have a natural light, and then you have a polarizer. That's a polarizing light. But then let's say, for example, you have 2 polarizer and analyzer, and their transmission axes are matching. Okay, that means, you see the same light. Okay. But then if you, let's say, if you rotate the analyzer, then its transmission axis is different compared to the analyzer. So then light is dimmer until, polarizer and analyzer have transmission axes that are perpendicular to one another. Then you see basically no light. Right, so you can see, right? So that's why. So the theta, basically in a way refers to transmission axis of the polarizer and analyzer, because the light that's coming out of the polarizer will always line up with the polarizer. Okay, and then you're looking at that axis, right, relative to the analyzer axis, and the theta represents that. All right, so let's look at an example here. So a plane polarized light is incident on a single polarizing disk with the direction of E naught parallel to the direction of the transmission axis. Through what angle should the disk be rotated so that intensity in the transmission beam is reduced by a factor of 3, 5, and 10? Those are the A, B, and C options. Right? All right, so one thing we know here is that we already have that it's a plane polarized light, so it's sort of like a 2-dimensional, right? So, but it's a polarized light, and it's a incident on a single polarizing disk. So you can think of it like as a circular. Okay, that means we're already dealing with the polarized light. So now what I can then use here is, because now it's going to go through another another polarizer like analyzer, then I can use the Mauss's law. I is equals to then I max then cosine squared theta. Okay, remember my goal here is to find um, those the beam being reduced by a factor of 3, 5, and 10. Okay, so that means what should the angle be so that I have that. All right, so which means what I'm looking at for part A is when I over I max, because it gives me as a a factor of 3, so like a ratio. So this is equals to since it's factor of 3, that means it's 1/3, right? So let's say we want this to be 1/3. Well, which means that in this equation, if I do I over I max, then this is equal to then cosine squared theta. All right, so then from this equation, if I then square both sides, then I get I over I max, right? Um, sorry, not square, but take the square root. Okay, so I over I max then is equals to then cosine of theta. Okay, then I can say then inverse cosine of the square root of I over I max. Okay, that's how I would calculate then this theta. Okay, so the first one is factor of 1/3. This means using this equation, theta is equals to inverse cosine of square root of basically 1/3, right? Because I over I max is 1/3. Okay, so then this will give me 54.7 degrees. Part B, I over I max then is equals to 1 over 5, 1/5. So then this will give me theta is equals to inverse cosine of square root of 1/5. Then this will give me 63.4 degrees. And then part C, I over I max is equals to 1 over 10. So then this will give me theta equals inverse cosine of square root of 1 over 10. So then this will give me 71.6 degrees. That means those are the polarizing axes that I need to get those, this type of, transmission uh, beam reduction in, let's say ratios. All right, so here's another example. Unpolarized light passes through two ideal Polaroid sheets. The axis of the first is vertical. The axis of the second is 30 point. Well, this is basically degrees, 30 degrees to the vertical. What fraction of the incident light is transmitted? Right. So let's think of it like this. So we have unpolarized light, which means that it has both axes propagating, and then it goes then through the first polarizer. Okay. It says the first polarizer has a vertical transmission axis. That means let's draw this here as a vertical. Okay. And it's generally easy to kind of like put this as point one, point one. That's the region where you have unpolarized light. Then let's say it kind of goes like this. Then that's what I have the second polarizer. And let's say then the light is going to continue like that. All right, so then this is then region 2. And when the polarized light goes through the first polarizer, then its axis can always match the polarizer axis. That means the light now going to be vertical like this. And then the second one, we are told, has 30 degrees to the vertical. That means it's going to be like this. That means when the light goes through the second polarizer, the analyzer, right? So that's going to be angle of 30 degrees with that. All right, so now let's see what we have. So this is I1, which is going to be I naught. This is then I2, which is going to be 1/2 I naught, right? So because the light going through the first polarizer loses the half of intensity. Then here, let's call this I3, right? 0.3. Then this will be then I max, then times cosine squared theta. All right. So now, what I have here is I max is basically the intensity before, basically in region 2, which is 1/2 I naught. Okay, so it's 1/2 I naught. Okay, in a way you can kind of like think of it like that, right? Then what I have here is cosine squared theta is, because now I have a 30 degrees, so cosine squared theta, if I put 30 degrees, so then for here I'm going to get 3/4. Okay, that means my equation becomes like this: I3, that means intensity is region 3, is equals to 1/2 times intensity at basically region 1, right? So basically 1/2 times maximum intensity, then times then cosine squared theta, or sorry, then for the cosine squared theta, basically I put like 3/4. Okay, but what we want here is what fraction. Again, that means I just do a ratio. That means divide both sides by I naught. Then what I get here is I get 1/2. So that's basically the intensity decrease in region 2. Then times 3/4, and that's the intensity decrease in region 3. And then calculating together, I get 0.375. That means you're only going to have roughly 37.5 or 38% of the original intensity. That means here you get 50%, and then here you get, let's say, 37.5% decrease. That means you end up with only about 37% of your intensity, original intensity, at that position. Another way we can polarize light is by reflection. Okay, so this is generally when the natural or unpolarized light goes from medium with one index of refraction to another which has a N2, right, a different index of refraction. Remember, some of the light will reflect, some of them will refract. Now, one thing we have here is this. So the polarization of reflected light, that means we're going to talk about reflected light. So because this is polarization by reflection. So if the angle of incident is 0, reflected beam is unpolarized. That means if it comes in like this, and then light goes back a little bit like that, reflected and refracted, this is not polarized. Okay. For other angles of incidence, so let's say where the theta 1 is not 0, reflected light polarized to some extent. Okay, there's a partial polarization, we call. And for one particular angle of incident, reflected light completely polarized. Okay, that means for some theta 1, remember, so this is theta incident, this is theta reflected, and according to the law of reflection, they're the same. That means they equal to theta 1. Okay, and this is theta 2, the light the refracted light, right? Now, the polarization of entire beam can be described by two electric field components. There is a parallel component, reflected more strongly than the other component. So result, you have partially polarized reflected beam and a refracted beam. So you can see, right? So let me kind of get rid of this. So those are, in terms of those dots represented electric field. So the dots are like toward you and into the page, right? So those represent electric field oscillating parallel to the reflecting surface and and perpendicular to the page. Okay. So that means those parallel reflect more strongly than the other components, which are the arrows like this, right? So the result, partial polarized reflected beam. And reflected beam also partially polarized, refracted beam, sorry. Now, then what we have here is we have special, angle. We call it polarizing angle. That means the angle of incidence varies until angle between reflected and refracted beam is 90 degrees. That means if we change this theta 1, theta 2 changes. And then obviously, because, theta 1 here and there exactly the same, that means reflected and refracted at some point can be perpendicular to one another. That means refracted beam only reflected beam completely polarized. In that case, reflected is completely polarized, refracted partially polarized. And angle of incidence at which the polarization occurs, basically this polarizing angle theta p, right, is given basically with this equation. So theta p plus 90 plus theta 2, which is, equals 180, right? So theta p plus 90 plus theta 2, that's basically gives you that angle 180 degrees. That means we can calculate the theta 2 by doing 90 minus theta p, because this 90 and 180 gives you 90, then theta 2 equals 90 minus theta p. Okay. And then we put this on a Snell's law equation, n2 over n1 equals sine of theta 1 over theta 2, right? Then theta 1 is equals to theta p. So then that becomes theta, sine of theta p divided by sine of theta 2. And obviously then theta 2 is equals to that. So you can see from that, right? Since sine of theta 2 equals sine of 90 minus theta p, that's, from one of those trig identities equals to cosine of theta p. So which means, in this case, we're going to call this theta p as the Brewster's angle. So then n2 over n1 equals sine of theta p over cosine of theta p. Okay. So the discoverer is the Scottish physicist and mathematician David Brewster. So then we call this angle theta p Brewster's angle. That means Brewster's angle is when the light, reflected light, is completely polarized. And it happens when reflected and refracted lights are perpendicular to one another. Right. So you can write n varies with wavelength for a given substance. So Brewster angle is also a function of wavelength. Okay. So that we know, from the previous equation, because let's say n is equals to wavelength in vacuum over wavelength in that medium. All right. So again, this equation then can be used to calculate that Brewster's angle, which sine of p over cosine of p is usually tangent of p, and then we kind of have this final equation for the calculation of theta p, which is the inverse tangent of the n2 over n1. Okay. All right, so here's an example then. Light in air strikes a water surface at the polarizing angle. The part of the beam refracted into the water strikes and submerged slab of material with refractive index n equals 1.62 as shown in the figure. The light reflected from the upper surface of the slab is completely polarized. Okay. So then find the angle theta between the water surface and the surface of the slab. All right, so let's see then what we have over here. One of the things we're going to do here is we know that the light strikes the liquid. That means this is, let's say, air, right? So let's say I can say that n1 is equals to 1, which is that's the air. And then you have then n2 is equals to 1.33. And then this is a glass with 1.62. Okay, so that's kind of what we have. So from here, we can look at it in terms of you have theta p representing that the light hitting the water from air at the Brewster's angle, right? Theta p, which means that we know that those two are perpendicular to one another. Okay, and then we can think of it like this. So let me maybe use a little bit different color. All right. So this is theta 2, and then this is theta 3. Okay, theta 2, this is theta 3. Now, then one thing we can have here is we can then have this, you can see, right, there's also the theta over there, which is the angle that, slab makes with water. Okay. So then they're all related where the theta plus 90 degrees plus theta 2, right? So 90 plus theta 2 plus the 90 degrees minus theta 3, and this is equals to 180. All right. That means, if we calculate that, so that's the relationship we'll get. All right, so from some algebra then, we can, since 90 plus 90 is 180, I have 180 over there, then what we end up with, theta plus theta2 minus theta3 equals 0, then theta is equals to the difference between theta3 and theta2. Okay. All right, so now that we have that, our goal will be then to go and find those theta3 and theta2 so we can do this calculation. So in terms of then, we can calculate, theta p. Let's say theta p here is using the equation for the Brewster's angle. Tangent of theta p is equals to um, index over fraction of water divided by index over fraction of air. So this will be 1.33 divided by 1. So, which is like 1.33. Then using inverse tangent of 1.33, we'll get then theta p to be 53.1 degrees. Okay. Then what I can say here is, now that I have theta p, and I know the medium index over fraction of 1 and 2, I can then easily solve for 2 using the Snell's law. So n1 sine of theta 1 equals n2 sine of theta 2, where theta 1 is theta p. So then I can solve for theta 2, which will equals to inverse sine of theta p, which is 53.1 divided by index of fraction of water, 1.33. So then theta 2 here is equals to 36.9 degrees. So that's one thing I needed. Then for the water to slab interface, okay. Then what I have here is using again Brewster's angle, tangent of theta 3 is, since that's same as this one, theta 3, right? So this is equals to then tangent of theta p, so which is equals to index over fraction of that slab divided by index over fraction of water. And we have that information, right? So it's 1.62 over 1.33. So then using that, we can calculate theta 3 to be 50.6 degrees. So we got that as well. Then we go back here and say, all right, so now that I have those, I have theta 3, which is 50.6 degrees, minus theta 2, which is 36.9 degrees, then get 13.7 degrees as the angle theta. All right, so that will be the angle between water surface and the surface of the slab. All right, so then the last thing here we have is the polarization by scattering. Okay, so this one, where the sunlight, let's say, comes and enters our atmosphere, then the air molecules basically absorb and remit the light. And what happens here is then the light that, remember, so the natural light from the sun has all the colors of the rainbow, right? And some of the molecules basically absorb the photons of light, but they don't necessarily absorb all of them, or not all of them at the same rate. So one thing we have here is when they absorb, generally, a smaller the wavelength of the particular light, more it is being absorbed. And one thing we know here is that, for example, red color has a longer wavelength than the violet color. Violet color from the visible spectrum of the light, right, is the shortest wavelength. And then the red is the longer wavelength. So that means, this absorption and re-radiation or re-emission of light by electrons in air molecules is what we call polarization by scattering. Okay, that means all the the electrons, right, all the molecules and things like that in our atmosphere, they absorb and they re-emit. Sometimes they re-emit in our direction, sometimes in a different direction, but that the idea here is that generally, for example, red you know, can go through the air molecules without being scattered too much. But for example, the smaller wavelength light, violet and blue, end up being, much more scattered. The violet obviously being the most. So then the sunlight becomes polarized when scattered. So similar to creating completely polarized light upon reflection from a surface Brewster's angle. Now the unpolarized beam of sunlight traveling in horizontal directions, right, molecular of gas, setting electrons of molecule into vibration. Then what we have here is that you can think, like, let's say there are two types of vibration, right? So you have the horizontal and vertical, vibration for the air molecules. Now, vibrating charges act like vibrating charges in antenna. So we have horizontal components of electric field vector. In incident wave result in horizontal components of vibrating charges, and then the vertical component of the vertical results in the vertical component of vibration. So then when you look at the, let's say, when you look at the light, right, you are basically looking at a different, direction vibration light. So if observer looks at the direction perpendicular to the original direction of the propagation of light, so then you see the vertical oscillating of charges send no radiation toward the observer, and observer sees light completely polarized in horizontal direction. So this does, orange arrows over there. Okay. So if the observer looks in other direction, light partially polarized in horizontal direction. Okay. So now, um, so what we have here is, as I mentioned, right, the wavelength of each color is different. Okay. So okay, right. So the light of various wavelengths, incident on gas, molecules of diameter. So if diameter, much smaller than the wavelength, then the relative intensity of scattered light varies as 1 over lambda to the 4. Okay. So then what we have here, we have oxygen, we have nitrogen molecules, right? And their diameter about roughly about 0.2 nanometers. So that means the light has to be comparable to that in order to be absorbed. So that's why the violet is being the smallest wavelength, is being absorbed more, is being absorbed and re-emitted more. So basically scattered more. Okay. So, and that's why, for example, when we look at the sky, we look at the most, let's say the absorbed and scattered light. But obviously, our eyes are not sensitive to violet, which is the most. So then we see the second most, which is the blue. So that's why when you look at the sky, right, during the daytime, you see blue, because blue is the most scattered, light that is, our eyes are sensitive to. Okay. So the red, in a way, thing like this, right? So if you're here, okay, so then they're all coming in. So for example, see, let's say these are the red. The red coming in and they're not being absorbed. For example, then you see one red. This goes here, this goes there. So then you see one red. But then what you have is that then the blue becomes scattered a lot. So it becomes scattered a lot. And then you have a blue coming from one molecule, then another one, another one. So then what you see, you see much more blue because they're being scattered and moving, let's say, in your direction, where you can see that, let's say, only red, like one of the reds moving toward your direction. So you see way more blue than you see red or other colors. So that's why to you, the skies appear to be blue, because where when you look at the sky, you see, like, let's say maybe a billion times more blue, let's say the photons reaching your eye, because they're being absorbed and re-emitted in random direction. Okay. So again, short wavelength radiation scattered more intensely than long wavelength. All right, so then that's kind of like that. So when you look at the sky and you see scattered light, violet, but our eyes don't see the violet, so we see blue. Okay. And our eyes is basically much more sensitive to that. Well, that's definitely not the blue skies, but that's pretty much would be what you see during the sunset. If you look toward the west at sunset, you're looking in the direction towards sun. So let's say then why do you see red? Sunset are red, let's say, compared to the daytime when it's blue. Well, it depends on in terms of how they scatter, right? In this case, most blue light has been scattered by air between you and the sun and things like this. So let's say when you're here, the sun is not coming like directly like that, but it's going like this. So sun is somewhere over here, right? So then what you see that the blue that being scattered, most of them kind of like scattered like this, but the red kind of moves toward you. So that means now it is dominated by red because, since you're here, most of the blue then is scattered somewhere over here, and you only see more red than blue. Okay, so that's why the most blue light has been scattered by air between you and the sun, and light that survives, much of its blue component scattered and heavily weighed towards red end of the spectrum. Result, you see red and orange colors of sunset or sunrise, right? But when the sun is more overhead, then obviously you see more blue scattered light than you see, let's say, a red color. All right, so then this concludes our chapter.